Now we move to the last major topic in our study of planetary interiors, and here the topic is interior heating. The temperature of the interior is one of the most important things that drives everything we'll be covering about planets and moons for the rest of the course. Surface processes like volcanic activity depend on interior heat. Even atmosphere formation depends on it. So this is going to keep coming up time and time again as we continue our study of what shapes worlds.
The key dividing line here is whether or not the interior is close to the melting point. It doesn't have to be liquid, so long as the temperature is approaching that melting point. Then the interior will be hot enough that the heat energy will have an important role in shaping the surface. But notice that I haven't given a specific temperature here. That's because several things play a role in determining how hot the melting point is in a world. The biggest factor will be composition. For example, ice melts at a much lower temperature than rock, so it takes a lot less heat to melt an icy world than it does to melt a rocky one.
This creates a bit of a paradox. It's easier for volcanoes and earthquakes to develop on small icy moons in the outer solar system than it is on larger rocky worlds close to the sun. From a geological standpoint, these icy worlds behave like warmer bodies than the much hotter rocky ones do, just because so little heat is needed to get that ice moving.
To start with, we should look at where the heat comes from in worlds. There are several possible sources depending on the type and composition of the planet or moon. But first, I want to give you the punchline for the entire chapter. Large worlds stay hot longer. This is the key idea that will carry forward into the rest of the course. Now, let's start with where the heat comes from. I'd like to start by looking at the heat sources that were important in the distant past. These came as a direct result of the way planets formed, and they were most important in the first billion years or less of solar system history. Both of these heat sources rely on the same basic energy transfer, converting gravitational energy into thermal energy. In other words, something falls, and the energy released turns into heat.
The first of these heat sources is accretion. We learned about accretion in the last chapter. It's the buildup of a planet or moon through collisions. Each of those collisions carries energy, so the more accretion, the more heat builds up inside the growing world. Notice that I'm including both solid body and gas accretion here. They both have the effect of dropping matter onto a planet and releasing heat as they do so.
The other heat source is differentiation. Early in this lecture, we saw that differentiation is the separation of a planet or moon into layers. As this happens, the densest materials, like iron, sink to the center of the world. In effect, this dense matter is continuing to fall towards the core. As it does this, it once again converts some of its gravitational energy into heat. Both differentiation and accretion occurred all over the solar system while the planets were forming, and for a short time afterwards. Since then, they haven't been very important, except in a few special circumstances. However, 3 other heat sources are still generating a lot of heat in worlds around the solar system today. Each of these dominates in a different population of worlds.
In terrestrial planets, the main heat source is the decay of radioactive elements. As we saw in the last chapter, the decay of common radioactive elements like uranium releases energy. In terrestrial planets, this radioactive material is common enough that it can be an important heat source. That's because most radioactive elements are concentrated in rock. Very few of them are found in ices or gases. So as the heat from accretion and differentiation dissipates, radioactive decay dominates the interior heat for these worlds.
In the moons of the Jovian planets, the main heat source is tidal heating. Back when we were discussing tides, we saw that planets and moons undergo tidal evolution, in which their energy of motion and spin is converted into heat. In the case of the moons of the giant planets, this is the dominant heat source. It's important here because of the complex tidal interactions that occur when many different moons are orbiting the same giant planet, so they can tug on each other, as well as feeling the tidal forces from the planet. There can also be some radioactive heating due to the rock in these worlds, but tides tend to dominate. Finally, the most important heat source in the Jovian planets is contraction heating. Since this is a new process, let's examine it a little more closely.
We've already seen that giant planets are compressed by their own weight. Over time, as heat energy flows out of these worlds, they shrink inward on themselves. However, as they shrink, this causes the outer layers to slowly fall towards the center. As we know, anytime something falls, it loses gravitational potential energy. This energy is being converted into heat, keeping the interiors of these giant planets hot. Of course, contraction heating only works on planets that are made of highly compressible materials, like hydrogen and helium. That's why it's only important in the giant planets. Interior heating will be important throughout the rest of the course, so this making sense table asks you to organize the different forms of interior heating we've just gone over.
Now that we know where the heat comes from, we need to look at what happens to it. How does it get out of the planet? In general, there are 3 ways heat can flow inside a body.
The first and the slowest of these is conduction. This is heat traveling through direct physical contact. Simply put, the fast-moving atoms in the hotter material bump up against the slower-moving atoms in the cooler material, and the result is that the cooler material heats up. This is the sort of heat flow we experience when we touch a hot object, like a hot cup of tea. The fast-moving atoms in the cup bump into and speed up the motion of the atoms in our hand, warming our hand.
The next way heat flows is through convection. Convection involves heat moving because it's carried along by moving fluids. When you heat up a liquid or gas, it expands and gets less dense. If you heat it from below, then that less dense fluid will start to float upward to get above the cooler, denser fluid. So this will carry heat upward with it. If you heat up a pot of soup on the stove, you can watch this happening, with the hotter soup rising to the surface and the cooler soup sinking down to replace it. This is also why we say that heat rises. The air in a room goes through convection, so that the warm air rises to the ceiling.
The last way to transfer heat is called radiation. In radiation, light carries the energy through or out of an object. That's not important inside planets. They're not hot enough for that. But it's very important inside stars. Convection and conduction dominate the interiors of planets and moons. Because convection carries heat more quickly, if it can happen, it will dominate. But it depends upon the material being a fluid. In other words, the interior has to be gas, liquid, or close enough to a liquid that it flows very slowly, something like silly putty. So this creates a natural division between worlds in the way that heat flows. Worlds with hotter interiors are more likely to be fluid enough for convection, so that's the way most heat flows through them. Worlds that are cooler are more rigid inside, so convection can't happen, and the only way heat can flow is through conduction. As we mentioned before, radiation doesn't play a role in moving heat inside planets, but it is the main way heat is lost from the surface of the planet out into space.
Now let's see how size affects how heat flows out of a world. First off, it's important to realize that heat flows slowly inside worlds. It takes hundreds of millions to billions of years for heat to work its way from the deep interior to the surface of even a small planet like the Earth. If we compare 2 worlds with similar compositions but different sizes, like the Earth and the Moon, we notice that the Moon has only 1/4 the radius of the Earth. This means that in the time it takes a given amount of heat to flow from the core to the surface of the Moon, the same amount of heat will be just 1/4 of the way to the Earth's surface. So it takes a much shorter time for heat to escape from a small world, like the Moon, than from a large world, like the Earth. The effect of this is that larger worlds stay hot much longer than smaller worlds.
Consider the terrestrial planets. The largest terrestrials, Earth and Venus, are quite hot inside. We can see the effects of this in their geologically active surfaces, which we'll look at more closely in the next lecture. On the other hand, the Moon and Mercury have mostly dead surfaces, indicating much cooler interiors. There's very little heat flowing up from inside these worlds. Mars is intermediate in size and intermediate in internal heat. It seems to be mostly cooled off now, but it was hot for much longer than Mercury or the Moon, so its surface shows many more signs of active geological processes.
Of course, a very active heat source, like strong tidal heating, can create exceptions here. Jupiter's moon Io is only slightly bigger than the Earth's moon, but it's very hot inside because so much tidal heat is being pumped into it. Finally, notice one thing we've left entirely out of this discussion of interior heating: the sun. The sun just doesn't matter as a heat source for the interiors of planets. It's very important at the surface, as we experience every day, but inside a planet, the sun doesn't make enough difference to play a role in deciding whether or not a planet is hot enough to be geologically active.
Find the copy of this Your Turn that you started in the Solar System slide set. You should have the first 3 columns completed for worlds we have discussed. Now complete the column on heat and convection. Depending on your section and instructor, you may be required to turn it in. In any case, it will be helpful for homework and review. So now let's see if you've got the key idea with heating. Consider a terrestrial planet that is 2.3 AU from its star and has a mass of 1.4 Earth masses. Should it be hot enough to be geologically active? What should the heat source be? See if you can figure it out. I've listed some data for our own terrestrial planets so you can compare.